Hi, everybody. Happy Monday. This is lecture 19. Today is Monday the 13th. We're going to be discussing section 3.4 in Stewart. I want to look ahead to Friday. Friday is exam 2. And I want to remind you of the study guide that you can find on the exam, on the web page. So if you click on that study guide, you'll find stuff. 10 problems as the previous exam, and 5 problems using derivatives of various methods. But notice that's something that's not on here, section 3.7. So we probably won't get to section 3.7 before the exam. If we do, it'll be on Wednesday. So it won't be on the exam. It'll be on the final, but it won't be on, or it'll be on the next midterm and it'll be on the final, but it won't be on this midterm. And then, so 5 problems about finding derivatives, and then 5 problems about using derivatives to do other things. All right. There are really 5 topics that need to be covered for section 3.4. One is an introduction to what are called differential equations, and then that's the first topic. And the second topic is introduction to what's called exponential growth. And then the remaining 3 topics are 3 kinds of examples. An example involving population of cell cultures from biology, an example involving radioactive decay from physics, and examples involving heating and cooling from physics. So the book has really nice examples of all 3 of those types. Actually, there's a 4th type of example in the book section having to do with bank account interest. And so I'm going to get to one of those kinds of examples today. I'm going to spend most of my time on the first 2 things, kind of an introduction to this topic. So meeting part 1, I'm going to call just Introduction to Differential Equations. So I want to start with a question. Question posed in the form of, here's a term, see if you can tell me what it means. So these words, f of x is proportional to g of x. Raise your hand if you know what those words mean. Got one hand up. Go ahead.
The result of the function f of x will always be the same in proportion to g of x. So like if f of x of a certain answer is 1 and g of x of a certain x is 3, then all answers for f of x over g of x will be 1/3.
Yeah, pretty good. You did sort of cave and use the word proportion in your. Anybody watch Schitt's Creek, the show? Remember the show where there's the what's his name, and is it Daniel and his mom are making a recipe and it calls for folding it in, and he asks her to explain what it is, and she says, well, it's like when you fold it in, and she turns out she's incapable of actually describing what it means to fold in. So it ends up, Daniel just keeps getting more and more mad. He says, you are not allowed to say the words fold in. But then what you ended up saying is exactly right. So, but I'm going to generalize it. F of x equals k times g of x for some real number constant, k. So the example you said was if f is 1/3 of g, it's always going to be 1/3 of g. So in other words, in that case, the number k would be 1/3. What do these words mean? F of x is inversely proportional to g of x. Well, the meaning of that is f of x equals k times 1/g of x. Now, neither one of these things, well, the words inversely proportional to, probably a lot of people don't have any idea what that is. But the words proportional to, you might sort of overlook the significance of this being the definition. But the significance of this definition is all the other stuff that the words don't mean. So there are a lot of times in common English usage where people will throw around the word proportional, and it doesn't reference this definition at all. So, you talk about a proportional response to something. Well, that just means, if somebody did something big, then you do something big. It's not this, or people. The thing is, g of x is not being squared here. There's no square root. There's no other thing going on, just f of x and g of x. So from now on in the sciences, realize that when you say that something is proportional to something else, it means exactly that. It doesn't mean anything else. Okay. So a particular use of this terminology. The rate of change of f is proportional to f of x. So these are the words. So what do those words have to mean? Exactly. So f prime of x equals k times f of x for some real number constant k. This is an example of what's called a differential equation? It's an equation that involves a function and its derivatives. So a differential equation is an equation that involves not a variable, but rather a function and its derivatives. So that's different from an equation involving a variable. Now, for equations involving variables, a solution of an equation would be a value for the variable that makes the equation true. Well, for differential equations, what we call a solution of a differential equation is something slightly different. So here are the words. F of x is a solution of the differential equation. That's one sentence. F of x is a solution of the differential equation. Or these words, f of x satisfies the differential equation. I'm going to abbreviate differential equation as DE. And what it means is when f and its derivative are substituted into that equation, you get a new equation that's actually true. So when f of x and its derivative f prime of x are substituted into that equation, you get something that's true. So when they're substituted into the differential equation, the result is a true equation. So for example, I want to consider that differential equation, this particular one. Now in general, differential equations can be quite messy. They can involve higher derivatives. So for the differential equation, f prime of x equals k times f of x. Question A, is f of x equals x squared a solution? Well, that means we're asking this. If I substitute f and its derivative into that equation, do I get something that's true? Well, let's see. The left side is f prime of x. So that's 2x. The right side is k f of x. So that's k times x squared. So when I substitute those, when I put those together, we see the equation 2x equals k x squared. That's not true. So the answer is this function is not a solution. Okay, let's do question B. Ooh, somebody brought down a new eraser for me. B, is f of x equals sine x a solution? Well, let's see. F prime of x is, so this is the left side. Is f prime of x, and that's going to be cos x. The right side is going to be k times f of x. So that's going to be k sine of x. So the equation, when I substitute those into the equation, the equation becomes cos x equals k sine of x. That's not true. So the answer is this is not a solution. Now, I want to stress what we're doing here. We're just as you would test to see if a number is a solution to an equation involving a variable, you would test that by substituting the number in and see if you get a true equation. We're doing the exact same thing with this differential equation and with functions. We're substituting functions into that equation to see if they create a new equation that's true. So C, is f of x equals c times e to the kx a solution? So c and k are constants. Well, let's check. I'm going to start by just building the left side. So the left side is f prime of x. And so that's the derivative of c e to the kx. Okay, well, c is a constant, so I can use the constant multiple rule. So I get c times the derivative of e to the kx. And then here, what rule do I use? Famous song by David Bowie. Okay, not quite. Homonym. What? Chain rule, yeah. Famous song is Changes. So chain rule. So my inner of x is the thing inside, so kx. So what's my inner prime? K. What's my outer function, somebody? E to the parentheses. So what's my outer prime? Good. So the derivative of e to the x is e to the x. The derivative of e to the t is e to the t. The derivative of e to the parentheses is e to the parentheses. Okay, so I'm going to use all those parts to assemble my derivative. So it's going to be c times my outer prime, so e to the parentheses. And I stuff them with my original inner function. And then I have to multiply by my inner prime. There it is. There's my derivative. Now I'm going to rearrange. I'm going to bring the k out front. K times c e to the kt. Now, anybody recognize part of that expression? Yeah.
Why did you put KT?
Yeah. Thank you. Now, anybody recognize part of that expression? What?
It's equal to the differential equation for k of x.
No, I'm just talking about part of that over there. What do you recognize in that expression? K and C are both constants, but look what this thing is. That's the expression for my f of x. So this is k times f of x. Oh, but that's the right side of the differential equation. So in fact, this function does satisfy the differential equation. So a big fact, so f of x equals c e to the kx is a solution. So big fact. Functions of this form, and this is a fact from the future. So if this were, 1670s Salem, Massachusetts, I could get burned at the stake for saying this thing from the future. But we know, we're going to find out, I can tell you in the future, you're going to find out that functions of this sort are the only functions that are solutions to that differential equation. Functions of this form are the only solutions to that differential equation. So that differential equation being that thing over there. Now, having said that, we're going to find out later in the hour that functions of this form can be disguised in many ways. This is the month of Halloween, so I guess it's fitting. But functions can look very different from, they might not be presented looking like c e to the kx, but they are in fact that form. So that's meeting part one, differential equations. Now, I have, most of my stories of my undergrad years are things that I didn't get when I was an undergrad. And this idea of what are solutions to differential equations. I didn't quite, somehow I was asleep that day or something. So, as of today, you know what a differential equation is, and you know what it means for something to be a solution of a differential equation. If you're looking for a solution of a differential equation, you're looking for a function that makes the differential equation true. Okay, so meeting part two is exponential growth and decay. Oops, I might have missed something in my... Can anybody read this? I can't even read it from here. Exponential growth and decay. So functions, systems whose size is described by a function of that form whose size is. So f of x, maybe I should say f of t equals c e to the k t. Are said to exhibit exponential growth when k is a positive number. Or exponential decay when k is negative. Now, I want to, today's sort of an important day because there's stuff that's happening today that's sort of taking out of common usage some words and reserving those words for certain things. So something growing exponentially from today on means this. So in common usage, people sling around the word exponential all the time. They just mean like something's growing really fast. Wow, it's growing exponentially. Well, I don't know. I mean, y equals x to the 1,000, that function grows really fast, but it does not grow exponentially. So you have to stop, as of today, stop using the words something's growing really fast unless you know that it's actually exhibiting exponential growth. And then you have to realize that you're going to be surrounded by people who speak sloppily, and you have to take what they say with a grain of salt. If somebody says something's growing exponentially or it's going exponentially fast, what does that even mean? Do they even know what the function is that's describing the behavior of that object? You're not supposed to use those words in the sciences unless you've got a function of this form. So it's kind of a bummer of a day because you're walking out of here with fewer words that you can sling around because exponential growth now means just that one thing. All right, so the constants c and k are significant. And so they get names, of course. So first of all, consider the initial value. If I have a function, if I have a system whose size is described by that function, that means at all time, for all time greater than or equal to 0, that's the function that describes the time of the system. So let's consider the initial size. So at time t equals 0. So I get f of 0 equals c e to the k times 0. So that's c e to the 0. So that's c times 1. That's just the number c. Oh, so in that formula, f of t equals c e to the kt, the letter c is telling you the initial value of the function. So constant c is called the initial value. And it's sometimes a different symbol, a more descriptive symbol is used instead of the letter c. So other more descriptive symbols are sometimes used. So I could say f of t equals f subscript 0 e to the kt. So that's the initial value, the subscript 0, and the fact that there's not a variable sitting here. It's just f subscript 0. It's supposed to remind you that this is just a number, that's the initial value. Or f subscript t equals f parentheses 0 e to the kt. Same thing, there's no variable here. This means I've already substituted in 0, and this is the initial value. So whatever the number is that's parked in front, that's the initial value. Next, consider the relative growth rate. So we have this differential equation which says f prime of x, or f prime, I'm going to say f prime of t equals c e to the kt. I'm sorry. F prime of t equals k times f of t. That's our differential equation. The rate of change of f is proportional to f. Let's divide both sides by f. And I get this, f prime of t over f of t is just this constant k. So this expression is called the relative growth rate. Now that's a useful thing to want to know. You know, like if I tell you that my net worth during this class period increased by $1,000, you think, wow, that's a lot of money. Well, not if I'm a trillionaire. You know, if I'm a trillionaire and my net worth only increased by $1,000 during this class period, then I'm not really doing very well. But if I'm only worth, if I'm only a millionaire and my net worth increased by $1,000 during this class period, that's pretty significant increase. So you want to know, not only how fast is something changing, but how fast is it changing relative to its size. So that's the idea of wanting to know about the relative growth rate. And you can see that for functions that have this behavior, they have constant relative growth rate. So again, we started this by having the phrase, the growth rate is proportional to the value of the function. And then now we have this other thing that comes right out of that. The relative growth rate is constant. So these, yeah.
Is E just Euler's number?
Yeah, yeah. So the following are synonymous. Synonymous. Having a brain, is that right? Let's have a vote. Is that the right way to spell synonymous? No? No clue? All right, this is now, from now on, this is how we spell synonymous in this class. Is that right? Good, all right. So, rate of change of f of t is proportional to f of t, or this, the relative growth rate is constant, or this. F of t has the form f of t equals c e to the kt. That is exponential growth. I'm writing these down because anybody here listen to WOUB radio? All right. There's a radio host on WOUB, Chris Riddle. He has a really deep voice. And he has this idea that he should mix it up. He shouldn't always say Ohio, so sometimes he says the Buckeye State. And he shouldn't always say West Virginia. Sometimes he says the Mountain State. So you'll get problems where you'll get these words in the description of the problem. You won't be hit over the head by saying a function is the form of exponential growth. You might just be told that some system has a constant relative growth rate. Oh, that's your clue that you're looking at one of these babies. Or you might be told that some system has a growth rate that's proportional to the population. Oh, that's your clue that you're dealing with a system that has exponential growth. Okay, dokes, so that's meeting part 2. Meeting part 3 is an example. So, as I said at the beginning of the hour, there are 3 kinds of examples. One example is involving population of a culture of cells. Another is involving exponential, or involving radioactive decay. And the third example is involving cooling. All right, so all three of these kinds of examples are in your homework. You've got homework problems about all three of those. And if you look in the book, all three of those are presented. Examples of all three of those kinds are presented in the book really well. So all that I'm going to do in class is the first type. I want to do one involving population. Before I start my example, I mentioned earlier that these functions have this standard form, but actually they can sort of be disguised. So variations on the form of f of t. And also, I want to remark on the sign of k. So for example, let's let f0 be 100, and let's let k be ln of 2. Then my function would be 100 e to the ln of 2 times t. There's my c e to the kt. But I can rewrite this. I can write this as e to the ln of 2 in parentheses times t, raised to the t power, because a to the b times c, remember that's a to the b raised to the c power. I can think of it that way. But what's e to the ln of 2? Two. Look how different that looks. That's an exponential. That's a system exhibiting exponential growth. It's actually of this form, but it's disguised to look this way. Now let's think about how this function would look. This would be an exponential function that has initial value at 100. So 0, 100 would be a point on this graph, and it's going up, and we don't really think about negative time. So there's my function. But if I wanted to, I imagine the left side of this equation would look like that, the left side of this function. Now let's let g of x with c equals 100 and k equals minus ln of 2. So g of t. So g of t equals 100 e to the minus ln of 2 times t. Well, let's rewrite this. So this is 100 times e to the minus ln of 2, all that in parentheses, raised to the t power. But that's 100 times 1 over e to the ln of 2, raised to the t power. And that's 100 times 1/2 to the t power. So notice I have a negative k. Remember I said k can be positive or negative. Now, so this is a function. Notice this is still of the form c e to the kt, but it's showing up, it's been presented in this weird way. How would the graph of this look? Well, let's go back to this. This function here, 100 e to the minus ln of 2t, looks just like this function, 100 e to the plus ln of 2t. But there's a minus sign inside by the variable. That's a transformation of the function that involves taking that graph and spinning it around the y-axis. So the graph of this function looks like this. What was the tail of that function sticking out on the left is going to be the right side of this function. And the missing left side is going to be this. So this graph is decaying. It's going down. So the negative k value gives rise to a function that's actually going down. This is exponential decay. All right. Now I want to do an example, and I'm not sure how far I'll get. We only have 10 minutes. So this is example 2. First example was that testing those various functions to see if they were satisfying that differential equation. So this example 2 is exercise 3.4, number 2. A bacteria culture grows with constant relative growth rate. Bacteria count was 400 at time 2 hours. So the population was 400 at t equals 2 hours. And the population was 25,600 at t equals 6 hours. So question A is, what is the relative growth rate? So notice this language, there's a bunch of very specific language here. Like, since when are we talking about relative growth rate? Well, I mean, what on earth does this have to do with this? Yeah.
Growth rate equals k.
Right, so the thing is, these words, constant relative growth rate, these words tell us that f of t equals f0, or I'm going to say p for population. P of t equals p0 e to the kt. Remember, I said there are these three things that are synonymous. Saying something has a growth rate that's proportional to its size, that's one way of saying it. Or to say that it has constant relative growth rate, that's another way of saying it. But they both mean that the function that obeys that is going to be of this form. And our question is to find k. Because the relative growth rate is this thing, k. Well, we're going to set up two equations. One is the population at time 2 hours is 400. We're told that. We're also told this. That's the translation into mathematical equations, this given information. So let's divide the second equation by the first equation. So if I divide that first equation by the second equation, notice a couple cool things. First of all, these cancel and I get 64. And over here on the right side, the p0's cancel. And I get e to the k6 divided by e to the k2. But that's the same as e to the k6 minus k2. And that's e to the k times 4. Now we take natural log of both sides. And I get, did everybody sign in? The sign-in sheet should be back and back somewhere. I get ln of 64 on the left, and on the right I get ln of e to the k times 4. But what is ln of e to the k times 4? One hand up. Yeah. Exactly. So now I divide both sides by 4. And I get this. There's my value of k. Question B is find the initial population. Oh, so notice, I've got a generic form, but now I've got an update. I know what k is. So let's update our form. So we know that p of t equals p0 times e to all that junk, ln of 64 over 4 times t. There's my e to the kt. So that's now what we know about our function. So question B is find the initial population. Okay, well, let's go back to this. The population at time 2 hours is 400. So we're going to use the fact that p of 2 equals 400. So I'm going to turn that around. I get 400 equals p of 2. And what is that? That's p0 e to the ln 64 over 4, sorry. Times t, which is 2. So 400 equals p0 e to the ln of 64 all over 2. So p0 equals 400 divided by e to the ln of 64 over 2. Now, this can be simplified e to the ln of 64 over 2, that's e to the ln of 64 times 1/2. Is that a 2 or a 4 down there? I think that's a tight. That's a 2. Okay. And so that's e to the ln of 64 raised to the 1/2 power. So that's 64 to the 1/2 power. That's just the number 8. Isn't that cool? So I end up with P0 equals 400 over 8. I think this is right, so that's 50. Not sure. Got to double check. Check. All right, we're out of time. Thank you all. So again, work on reading the book and read those book examples because the homework problems are based on those. And I'll see you on Wednesday.